we have talked about frequency distribution of the spot speed. We have also talked about the statistics calculated from it, and we have done the before and after studies. Now we are moving on to the chi-square test. Okay, before moving on to the test, the analysis which we have done before and after for the sample size, confidence interval, everything was based upon an assumption. The assumption was that spot speed data follows normal distribution. Okay, so spot speed data follows this sort of a distribution, bell-shaped curve, symmetrical in the peak in the center, and so on and so forth. Now this assumption is not yet mathematically checked. We just looked at the graph which was best fit. All the points were not on the graph. You can see it here. Okay. So why didn't I join all the points? Because I wanted the best fit curve. So I'm making it normal distribution then. Okay, so what is the actual proof that this is normal distribution data? So for the actual proof, we do a test which is called as a chi-square test. In the chi-square test, we need two things. So you remember we have speed groups. Okay, we have frequency distribution table, and in each in the table, each row is a group. I'm talking about this one. So these are the groups. Each row is a group, and in each row you have number of vehicles, right? This is my n. For the chi-square test, I need the n values, okay, and I also need something which is called as the theoretical frequency. Okay, so n is already observed from the field, and now I need the f value as well, which is the theoretical frequency. For that, we will do some pre-processing with the data. Now this is the same data for which we have done the example with mean, median, mode, standard deviation. Okay, the one for which we had the plots and everything. Okay, so the data is same. It is the same data, but we have done some rearranging with the data. Okay, what is the first thing? First of all, the speed groups are arranged from highest to lowest. So highest speed group on the top, lowest speed group on the bottom. Now the highest speed group had an upper limit. I removed that upper limit with infinity. So it was actually 64 to 66. So I remove 66 with infinity. Okay, whatever it is, I will remove it and I will write it as infinity here. Okay, I will do the opposite with the lower limit. Okay, the last group has a lower limit of whatever. Okay, and I will replace it with minus infinity. Okay, so the so the first group upper limit removed with infinity, last group lower limit removed with infinity. Okay, another thing which you don't see here, but I will show you from the table which you originally have, which is, now you see there's a group which has 0 values. Okay, and you can see there's a group which has 0 values at the start. Any groups which have 0 values at the ends, so if there is a group here which has 0 values, I will keep it, I will not remove it. But if any group at any of the end, either the highest end of the distribution or the lowest end of the distribution has 0 values, okay, then I will remove them. For the chi-square, I will remove them. Okay, so the first thing which I did was I rearranged the groups highest to lowest, and then I removed the upper limit and the lower limit with infinity. and then I remove the 0 groups if they were at the ends. Okay, if I remove those groups and whatever becomes the first group and the last group, I'll do the infinity with them. Okay, the infinity thing is done with the groups after removing the 0. Okay, so there was a 0 group 66 to 68 something, but it has 0 values. I removed it. Okay, and the last thing, the last one, same. Okay, I removed it from the end. Okay, and whatever the group is remaining, I remove the last limit, the lower limit with minus infinity. Okay, now the n values are coming from the original table. Okay, so whatever number of values were for the highest group, they were 2, so I wrote it here. The next one had 3, the next one 7. Okay, so these values are same as what are given in the actual data, so they are coming from the field. Then for each group, I'll take the upper limit and I will do this with it. Okay, this is sigma. Okay, maybe you cannot see clearly. Sigma means standard deviation. Okay, sigma means standard deviation. So I already calculated the mean and the standard deviation for this data set. We already did in the previous examples. Okay, so the mean of the data is 48.2 and the standard deviation is 6.14. Okay, so I will take the x as upper limit of every group. For the first group, x will be infinity. Because it's infinity, so infinity minus anything divided by anything is infinity. Okay, so infinity comes as it is because any mathematical operation you do with infinity remains the same. Okay, now for the second group, I'll put 64 here. Okay, so it will become 64 minus mean 48 upon sigma, which is 6.1. Okay, so the answer is 2.57. Okay, so 2.57 is 64 minus mean upon standard deviation. Okay, and the same continues. Okay, then 62, 60, 58 and so on and so forth. Only x will change, mean and standard deviation remains the same. So you got the z value, we are calling them the z values. Okay, now we have a z table as well. Z is a standard normal distribution. Okay, so I will take these z values to the z table, this one. Okay, how to read the z table? The first 2 digits on the first column, the third digit on the first row. First column, first row. Okay, so the first z value is 2.57. The first one is infinity. I will talk about it later on, but the first real z value is 2.57. Okay, so 2.5 here and 0.07 here. Okay, so put 2.5 from here, 0.07 from here, 2.57. So the probability is 0.9949. Okay, so in the next column I will write the probability. So 2.57 probability from the z table, 0.9949. Same thing for all of them. Okay, now if I go to find infinity in the z table, I will not find it. Okay, the maximum value here is 3.49. 3.49. The rule is any value more than 3.49, okay, the probability is 1, because these are cumulative probabilities. Cumulative. Okay, so probability can maximum go up to 1. Okay, so at 3.49 it goes up to 1, and after 1 it cannot increase, so it will remain 1. So now you can see here at infinity the probability is 1. Okay, it is 1. So if any value, I'm not talking only about infinity, any value which is more than 3.49, because 3.49 is the last value in the table. Any value which is more than that has a probability of 1, because cumulative probability cannot go more than 1. Okay, so even if I got 4 here in the second value, if I got 4 here or 5 here or 6 here, I'll write 1 again. Okay, Now negative values. There is a z table for negative values as well. Okay, so like it is showing for plus 2.57. There's another half of the table which shows it for minus 2.57. Okay, so you will see the minus written here. So in that case there will be no problem. Okay, but let's say I don't have the half of the table. Okay, the traffic book only gives this table and Dr. Oni is very lazy to go with the other half. Okay, so what we will do, so for example I have value of 0.03. Now this is my z value. I need probability for this z value. Okay, so what we will do here, I'll go to the z table and just look at the value. Value is 0.03. Forget about the minus. 0.03. 0.03 is 0.5120. So the probability for 0.03 is that value 0.03 is 0.5149. Where is it? 5120, sorry. 20. Okay. Now if I want the probability of negative 0.03, I'll do this 1 minus 0.5120. Okay. So when you want to convert the probability of negative to positive, you will do 1 minus the probability. Okay, don't do 1 minus 0.03. Okay, I did 1 minus the probability 0.5120, not 1 minus 0.03. Okay, 0.03 is the z value. So we are subtracting probability from 1, not the z value from 1. Okay, so for any value more than 3.49, you will put probability 1. Any value which is negative, you don't have the other half of the z table, you will take the probability from here and do 1 minus that. Okay, so this is what has been done here. Okay, 1 because of infinity, and this is when you do 1 minus the positive number. Okay, then the next column you will take, now these are cumulative probabilities as I mentioned, these are cumulative probabilities. Now I want the probability for each group now. So from cumulative to find out group, I'll do group 2 minus group 1, the probability of group 2 minus from probability of group 1. Probability group 2 minus probability group 1. Okay, so this is what we are putting in this table here. So the first one is group 2 minus group 1, 0.9149 minus 1. Second one is 0.9878 minus 1, minus this one, not 1. Okay, 0.9878 minus 0.9949. Okay, so in each case you will take the difference of the two values. Okay, difference of two values here, to here, to here, to here, and so on and so forth. Okay, so you got this one. Then the next one is you calculate theoretical frequency, the f value, the one which we also we need here for the chi-square. Okay, this is what we call as the chi-square. So I need the f values. So how do I convert the probability into f values? I'll take this number, multiply by the total of n. Sorry, total of n, this one. Okay, total of n is 368. It's the previous example, and we already did the total, it was 368. So each of these values from this column will be multiplied by 368. Okay, with the total only. So 0.0051 multiplied by 368, this value. 0.0071 multiplied by 368, this value. Okay, and so on and so forth. Now you got the f values. Okay. Now for every group I have n here and f here. So I can do this one. N and f, I can do this, but I have to perform a check. The check is all f values must be greater than or equal to 5. This is the check. Once you calculate the f values, you need to check if all of them are greater than or equal to 5 or not. If they are not, then you will merge the groups to make them 5. Okay, so you can see the first group and the second group, they don't have 5. I will merge them. If I merge them, they still don't become 5. 2 plus 6, 1.8, they don't become 5. They will be 4, maybe something. Okay, So even after one merging, it does not become 5. I'll do the next merging. I merge it with the next group. Okay. So I merged the first one with the second. Did I got 5? Did I get 5? No. I merged with the third one. Now I got 5 because 5 plus anything will be more than 5. So first I will have to merge first 3 groups. Do I have any value less than 5 here? Yes, the last two. So 3 plus 4, I merge them, they become more than 5. Okay. So now in this column, you will see the f values after merging. Okay. So the check was for the f value to make them more than 5. Now, after you did the check, you did the merging. If you didn't do the merging, this is your f and this is your n. If you didn't do the merging, the n and the f. Okay. If you did the merging for f, so this is your final f. Now you have to do the merging for n as well. So I cannot have one f value and 3 n values. Okay, I merge the 3 groups, so these 3 f become 1. I have to merge the 3 n values as well, so these 3 will become 1 as well. Okay, so 2 plus 3 plus 7, 12. Okay, and I did the merging for the last 2 groups, so last 2 n will be merged as well, this will become 10. Okay, so the first 3 were merged, first 3 n are merged, first last 2 f's are merged, last 2 n's are merged, and you got these values. Okay, now I can do this. Okay, so for each group I will do n minus f upon f, n minus f square upon f, and I will do the summation in the end. So this is for each group and this is the summation. Okay, anybody has any questions? I will tell you what to do with this, but if you have any questions up till this point, please let me know. Okay, moving on. Once you have the chi-square, I will go to a chi-square table. This is what we call the chi-square table. Now the chi-square values are in the table. Okay, the first column of this table represents the degrees of freedom. DF stands for degrees of freedom. DF stands for degrees of freedom. How do I get degrees of freedom? DF equals number of groups you have minus 3. DF stands for number of groups minus 3. Which groups? The speed groups you have. Okay, but the problem is we merged some of the groups. Okay, so those groups will be counted as 1 now. So these 3 will be counted as 1 group and the last 2 will be counted as 1 group. So now you have to count after merging. Okay, so if I count from here 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. Okay, so after merging I got 14 groups. Okay, so my degrees of freedom will be 14 minus 3, which is 11. Okay, so my chi-square is 11.669 and my degrees of freedom is 11. So I will go here 11. Okay, now I'm looking for 11.66 something. So 2.6, 3, 3.8, 4, 5 point something, 7 point something, 10 point something. Then I got 13. Okay, so 11.66 is between them. Okay, it's between them. Now I'll go to the first row. At 10.34 the probability is 0.5. At 13.7 the probability is 0.25. I need the probability for 11.6669. Okay, so when chi is 10.34, the probability is 0.5. Chi is 13.70. P is 0.25. When chi is 11.669, this is my value. What is the P? Tell me. What is the P value here? You will do interpolation, right? So what will be the P value? Yes, anyone with the interpolation. 0.395. Okay. So now I will tell you the rule. Now remember, we are checking if the speed follows normal distribution or not. The rule is, I'll tell you the rule. The rule is if this probability which you are telling me, zero point 0.3 whatever, if this probability is 5% or less, then the speed does not follow normal distribution. Okay, the rule is, it is written here, not written, it's written here. The probability which you got from the interpolation in this case, the p-value, it if it comes out to be 5% or less, then the speed does not follow normal distribution. In our case, it is more than 5%. Okay, whether it is 0.39 or whether it is 0.4. Okay, in both cases it is more than 5%. Okay, so the answer will not change. The speed follows normal distribution. Okay, speed follows normal distribution. Okay, so whenever you are checking any data with distribution, you perform chi-square, and the value of chi-square tells you how much is the difference between your data and the distribution. Okay, so if the difference is less, we say the data follows distribution. Difference is more, we say data does not follow normal distribution or the distribution. And what is our criteria? The p-value. Okay, when the p-value gets less than 5%, that means the difference has significantly increased between my data and the distribution. Okay, so now we say the data does not follow the normal distribution and vice versa. Okay, in this case, I asked you to do the interpolation, sorry for that. But in this case, if you are doing interpolation between 0.5 and 0.25, your answer will be always more than 5%. Okay, so even without the interpolation, you can tell me that the data follows normal distribution. Okay, so interpolation was just to wake you up or see who is already awake. But the point is, my target is 5%. So when I achieve this target or more, I'll say data follows normal distribution. Is it clear? Okay. This is an example given in the slides. Okay, it has all the parts which we have done up till now: frequency, distribution, okay, the plotting, the mean, median, mode, pace, okay, whatever we have done up till now. Okay, the chi-square as well, the confidence interval, the chi-square, sample size, okay, everything is there. At the end of the slides you will find question numbers for more problems from the book. Okay, so use them for your practice. Now we are moving to another topic which is relevant to speed, which is travel time. Okay, so travel time increases, speed decreases, so they are both related to each other, so we always discuss them together. A study which is done for travel time observation is also called as journey time surveys. A study done for travel time observations is also called as journey time surveys. Now you cannot calculate spot speed from travel time studies, from journey time surveys. Why? Because of the length. For spot speed, we have a limit of the length. Okay, that it must be a spot or it must be a short length of the highway. Okay, to do the spot speed. But journey time or travel time cannot be done for short distances. They must have full segments, full highways, or maybe just any between any 2 points which are far from each other. So it can be one point in Sakhir, the next one in Rifa. Okay, so but the point is, journey times surveys or travel time studies are not done on limited lengths of the highways. They are done for uh, longer routes. Okay, when you are doing the travel time studies, delay study is becomes a part of it, or can be made a part of it. Okay, so for travel time studies, delay is a part of it. So why do we do travel time studies? We do travel time studies to find out problem locations. Okay, what is a problem location which has high delay? Okay, high delay is a problem location. So uh, we do delay studies, the travel time study, to find out which one is the problem location. For measuring a level of service for an arterial, level of service means performance of the highway. So a higher travel time means lower performance, or a higher delay means lower performance, and so on and so forth. Travel time studies also provide input for traffic assignment models. Okay, what is traffic assignment model? You have the demand of the highway. Okay, calculating demand of the highway is called traffic assignment. Calculating demand of the highway is called traffic assignment. So we need to calculate the demand on the basis of selection of the driver, right? So if the driver has different choices, which highway he will or she will select. This depends upon what? The travel time. The decision of selection of the highway depends upon travel time. So when you know the travel time, you know if the driver will select this highway or not. Okay, so this is how it becomes the part of traffic assignment models. Travel time is also important for economic evaluation of the highway. Okay, how? If you are going to build a new highway, if you are going to build a new bridge, okay, so you have multiple options. You can go from this route, you can make the bridge on this location, on the other location. Okay, so which one you will choose? From these options, you will choose the one which gives you maximum saving of travel time. Okay, it gives you maximum saving of travel time. So when you are doing the evaluation of different options for the highways, you will always go for the option which gives you maximum saving of travel time, minimum meaning minimum travel time. Okay, and travel time studies are also used for developing travel time contour map. Okay, can somebody give me what is a contour map? Can somebody tell me what is a contour map? Yeah, you may have heard about it in surveying, right? So what did you hear about, or what did you know about uh, contour map from surveying? What did it tell you about contour map? Tell me. Elevation, a map showing elevation, right? So now you replace elevation with travel time. In a travel time contour map, you replace elevation with travel time. Okay. So we will see the contour map, and we will discuss why and where it is used later on. Okay, let us focus on how to collect travel time data. There are different studies to collect travel time data, okay, or journey time surveys. One of the technique is called test car technique. In a test car technique, a car is hired to move over the highway where you want the travel time, and an observer is sitting inside the car noting down the travel time. Okay, so we have a car with a driver, and then we have another person who is noting down the travel time. Okay, as the car moves, he is noting down how much time it is taking from one point to the other point to the other point. Okay, so now because the observer is inside the car, he can also note for how much time the car was stopped. Okay, so he can make two observations, one for travel time, the other one for separately from this travel time how much time the car was stopped. So you have the delay studies, like I said, this is the incorporation of delay within the travel time. Okay, now this technique can be applied in different ways according to your objective and the type of highway. according to your objective and the type of highway. Let's say your objective is to find out average travel speed on a two-lane highway. Okay, then the test car will be applied in a manner which is called as floating car. Okay, if you want to find out average travel speed on a two-lane highway, then test car becomes floating car. Okay, what is the meaning of floating car? You hire a car, like I said, the procedure is same. A car with a driver and observer inside the car, and but there is a instruction given to the driver. You are in a two-lane highway, so the other lane is for the direction. The other lane is for the other direction. In no case you will go to the other lane. Okay, or you should not in no case, but you should not try to go to the other lane unless you are overtaken by a driver. Okay, so you were driving in your lane, another driver came from the other lane and he overtook you, he came in front of you. Okay, so now you are allowed to overtake one car, any one car. Okay, that driver could be, you know, the Formula 1 driver, so don't try to overtake that driver, but anyone who you can overtake in the same observation, within the same observation. Okay, so till you reach the end point, you are allowed to overtake the number of cars which have overtaken you. So two cars have overtaken you, you can overtake two cars. One car has overtaken you, you can overtake one car. Okay, otherwise you will just keep on moving in your lane. If nobody has overtaken you, you will just keep on moving. Okay, so this is the concept of floating car. Then we have the maximum car. In maximum car, you are on a multi-lane highway and you are asking the driver to go at high speed. Okay, the purpose of this method is to get the 85th percentile of the highway. Okay, 85th percentile of the highway. This is the speed which we use in design, and this is the speed which we use for speed limits as well. Okay, so I want to know what is the suitable speed limit for a highway. I will, and it's a multi-lane highway, I will do the maximum car over there. Okay, so again maximum car is a variation of test car. Another variation of test car is average car. Average car is again on multi-lane highway, but the driver will drive normally. No instructions. No instructions about overtaking, no instructions about increasing the speed or decreasing the speed. Okay, so this is the most common one, the average car, variation of test car. Okay, so you have floating car for two-lane highways, average speed, multi-lane highways, maximum speed, maximum car, and average speed on multi-lane highways, average car. Okay, and in each case the instructions to the drivers change, but the setup remains the same. You have a car with a driver and an observer inside. Now this test car which you are putting on the highway, hiring for the observation, is an extra car. Okay, it's an extra car on the highway. In normal conditions, this car is not there, so it may have a small impact on the normal traffic volume. So if traffic volume changes, that means your travel time observation is also not real. Okay, so how many cars can I consider acceptable as test cars on the highway in one time? Okay, if I have only one car, the effect is very negligible, you can forget about it, no problem. Okay, two cars maybe, still no problem, but if I keep on increasing and increasing, at some point it will start to show the effect on the traffic. So I want to avoid that point. Okay, so they have given us some limits to avoid those points. In most of the cases, up to 6 cars is allowed. Okay, or even up to 10 cars is allowed in most of the cases. On major highways in the peak hours, so I'm talking about the average car method now. Okay, on major highways in the peak hours, even up to 50 cars will not have that much of an effect, because on major highways in the peak hour, the volume is already in thousands. So when it is already in thousands, your 50 cars will not have much effect. Okay, so this is these are the limits. Okay, beyond, if you go beyond these limits, there is a danger that your test cars are affecting traffic and your values are not the true values, the real values. Okay, another method of travel time study is license plate technique. In license plate technique, you have two observers, one at the start point, one at the end point. They note down the license plate number of the car and they note or the registration plate number of the car and the time at which the car has crossed them. Okay, so both the guys are noting the ID of the car and the time of the car. So later on they can match, okay, which ID started at what time and ended at what time. So they will know the travel time. So if ID XX started at 3 p.m. and it ended or reached the end point at 3:15 p.m., we know the travel time is 15 minutes. Okay, the problem with this technique is you don't get the delay. Okay, you don't know where the car stopped between the 2 points. Okay, another problem is matching of the ID numbers, the license plate numbers. The guy who is at the start point, he is noting down one car, but he is not noting down all the cars. He cannot, manually it's not possible. And the same missing will happen on the end point as well. So the guy who is at the end point, he's also noting down some cars and missing some cars. So maybe the first guy noted XX, the last guy missed XX, he was noting some other car at that point of time. Okay, so this sample is wasted. Okay, so the first guy may have 500 observations, the second guy also has 500 observations, but this doesn't mean we have 500 observations of travel time. Only the ones which are matching at both points will be used for calculating the travel time. So maybe after 500 only 100 are matching between the two guys. Okay, so in that case I have only 100 samples now, not 500. So you can see I took the time of 500, I only got 100 in the end. Okay, so this is an important issue here, not having the delay and the sample size. But I told you the advantage is you don't need a car, you don't need a driver, you only need two observers, and these observers are also standing on the side of the road, safe and sound with a pen and paper and so on. Other methods of doing this are you can use a camera, okay, or you can use an observer which can which can be positioned at a very large or very high point. Okay, we call it the vintage point. What is the vintage point? The point which gives you a good view of the whole segment. The point which gives you a good view of the whole segment, we call it the vintage view, vintage point. Okay, so if I'm standing at a very high point, I may be able to see the start point as well as the end point of my segment. Okay, so I know I can start my stopwatch from start to end for the same car. Okay, so I know, okay, the red car has entered, I start my watch, and when it will reach the end point I will stop it. I know the exact travel time, and I can track the stop time as well, that this car, okay, started but now it has stopped. I can note down the stop time as well. Okay, and the same thing can be done with a camera as well. So you don't have an observer at that time, you have a camera which is taking the video. Okay, later on you process the video. Okay, you process the video, you don't have to do it manually, you just look at the video. Okay, this car entered, I can see the time in the video, this car reached the other point this time, now let me rewind the video, I see another car, and so on and so forth. Okay, so in the case of a video, you can get all the cars which have crossed your camera. Okay, another method is, instead of having an observer in the car, you can have equipments which are measuring the distance and time and speed for you. Okay, so car already has a speedometer, odometer, but they are not recording, obviously. You can add some extra sensors, some extra trackers which can give you this. Okay, many companies have these trackers inside their cars from the start, because they want to track their vehicles, right? So the postal companies, the courier companies, okay, they have these trackers in their cars and in their trucks. Okay, so they already have it, so you don't need to, you can just take the data from the tracker, so you know how much distance it has covered, how much time it has taken, and so on and so forth. Okay, this is a table which gives you example of the which gives you example of the data which is taken by test car method. Okay, so in the on top of the table you see some details about the survey itself. Okay, when what is was it done, what date, by who, and what was the start point, and so on and so forth. On the first column you see checkpoints. What are checkpoints? The points which are coming in your way, any important point which is coming in your way. Okay, so you can divide your entire route, your entire segment into multiple checkpoints if they are important points. Okay, so in this case some of these points are signals. Okay, so in this way it can be done. So we are not just taking it from start to end, we are taking it from start to the first important point, then the next important point, the next important point, and so on and so forth. Okay, next one is cumulative distance. So we are measuring the distance as well, because in the end we may want to calculate the speed. Okay, so we are taking the at each checkpoint I have a distance measuring device, or maybe I'm using the odometer of the car to mark the distance. Okay, I already marked it maybe on the map, and when I cross that point I know I have covered that much distance. For example, in this case they already marked the point on the map that when you cross this point you have covered 1 mile. Okay, so when you cross this point 1 mile, cross this point 2 miles, cross this point 3 miles, and so on and so forth. So you can do it, like do it in advance uh, before you go in the field. Okay, so I know I cross this point 1 mile is done, and so on and so forth. Then for every point I'm taking the cumulative time. Okay, so keep in mind cumulative means it's from the start point. So both these columns are from the start point. This is distance from the start point, this is time from the start point. Okay, all of them are from the same point. And then we have the next observations which are for each section which meaning between two consecutive points, so the first observation is between this point and the last point. The next observation is between these 2 points. The next one is between these 2 points. Okay, and so on and so forth. Okay, what are these observations which are per section? Delay, stops, travel time, and reasons for delay. Basically they are calling them notes, but they are basically showing reasons for delay. Okay, so between the first point and this one, delay is 0, stop is 0, travel time is what you already know. Okay, between the next 2 points, delay is 0, the car did not stop, travel time is the difference of these two. From the start to this point 3 minutes 5 seconds, from start to the previous point 1 minute 35 seconds. So I take the difference, I get the travel time for this section only, between these 2 points only. Okay, next section between 17 and 18, delay 42.6 seconds, car stopped 3 times. Why did it stop? It stopped because of the signals. There were 3 signals in this 1 mile. Okay, and the travel time again 550 minus 305, yeah, 245. Okay, this is minutes and seconds, why they have written it like this? Because of the stopwatch. When you are looking at the time on a stopwatch, this is what it shows, this is how it shows, minutes and seconds separately. So this is how we are using it. Okay, so any questions up till here? Anybody has any questions? Okay, this is another sample from a Bahraini journey time survey. You can see it's slightly different. Okay, but it is still giving you, see the intermediate points, checkpoints, the distance, cumulative, and the time is also cumulative. Okay, and they have notes as well, how much was the delay and so on and so forth. Okay, so it's simpler, it has less values. Okay, how many times the car stopped, number of stops, these are not there, but the main things are there. The main things are distance, the cumulative travel time, and the reasons for delay. Okay, and you can see the details on the top here. Okay, now before we move on with any calculations, keep one thing in mind, we are still on the same chapter. We are still discussing the same chapter, spot speed. In the book, these examples for travel time are in the same chapter as spot speed. So we are not discussing any new equations here. We are just going to use the equations which we already seen for spot speed. Okay, so when you look at any equation here, don't think that you have not seen it. Okay, it's part of the same topic. Okay, so let's say you have an arterial which has a true mean running time of 196 seconds for a 3-mile section. The standard deviation of running time is 15 seconds. Okay, let us assume that this travel time follows normal distribution. Okay, the one which we set for spot speed as well. Okay, because time and speed are interrelated. So let us say that the travel time also follows normal distribution. Now what are they asking for? They are asking for mean running speed and the 95% confidence interval of running speed. First of all, we have running time. Running time is not the same as travel time. Okay, running time means travel time minus delay. Okay, so this is time without delay. They calculated the delay, they subtracted it, the remaining is called running time. Okay, secondly, they are giving me true mean running time. True mean running time means it is for the entire population. True mean running time means it is for the entire population. Then the standard deviation becomes a standard error. Remember, we discussed that standard deviation is represented with S, and standard error was represented with E, which was S upon square root of n. Okay, when you have a sample, but if you don't have a sample for the population, how do I know it's for the population? Because they said it is true mean running time. So true, the word true, okay, or true mean is for the population. So when data is given for the population, then E is S, standard deviation is directly the E value, the standard error. Okay, so now let us calculate the mean running time, mean running speed, and 95% confidence interval of speed. Remember, I'm using the same equation which we have used earlier. I have running time and I have 3-mile section. Okay, so mean running speed is distance upon time. Remember, distance upon time. So 3 miles distance upon time. Time is 196. Mean running time. It is in seconds. I want hours. So this one. This will give me mean running speed. Distance upon mean running time. And the time converted to hours. How much is this? Okay, so this is your mean running speed. Okay, now for 95% confidence interval of mean running speed, I have to calculate 95% confidence interval of running time. Okay, so 95% confidence interval of anything was mean plus minus 1.96 e. Okay, so if I'm doing it for the running time, the mean is 196 plus minus 1.96 and my E is 15 seconds, right? 15 seconds. So this will give me a 95% confidence interval of running time. Okay, how much is this? Yes. How much is this? Okay. Now, if you do the distance upon time with this interval, it will become the 95% confidence interval of speed. Okay. So, if I do the same which I did with the mean, distance upon time, 225.4. So, this will become the 95% confidence interval of running speed. Okay, so I was given mean time, I calculated mean speed. Then I calculated the confidence interval of time to calculate the confidence interval of speed. In all the cases, we are just doing distance upon time, and the time is converted to hours. Any questions? Anybody has any questions? Okay, I will stop.